Calculus BC, we are taking a look at 12.9, a tricky section, and 12.9, our worksheet that we had. Really just want to help some kids out. Let's just take a look at number 4, for example. We're asked to do this integral, and you might wonder how we can proceed doing that. Remember what we talked about. What you're actually looking for is, unless they're giving you a series to work with, you'd like to build a series in this section from that geometric series. So you might recall that we have this 1 all over 1 minus x. That's how we started the lesson out. That was 1 plus x squared, dot, 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 x to the nth. And we said, hey, this would be a sigma, a sum from n equals 0 to infinity of x sub n. You can see that nth term right in there. And what we talked about before is we, of course, have the ability to make substitutions. And wherever we have this x here, we can replace whatever we'd like. Now, first of all, why did I look at that 1 over 1 minus x? You might notice in this problem, the denominator is 1 minus something. It's not 1 minus a t, it's 1 minus t to the third. So that, by the way, then is going to lead us to say, you know what, instead of having an x, I want to have x to the 8th. And we could say 1 plus x to the 8th plus x to the 8th squared. You could see what's happening here. The next one would be x to the 8th to the third. Here's x to the 8th to the n. And forgive me, we should have dot, dot, dot. We have to be very clear that that's not the end of the series in the middle there. So I'm showing this term by term expansion. And up here, that got a little bit ugly. There's your sigma. So let's clean that up just a tad. You can see that this is going to be 1 plus x to the 8th. Powers to powers, we multiply. That's x to the 16th. You might not be too surprised to see every single term here is going to be a multiple of 8. By the way, you can always double check if you've done this correctly by expanding your sigma right here. Like plug in n equals 0 plus plug in n equals 1 and so forth. Now, right now, of course, we can refer back to this integrand, and you can say, well, wait a minute, this is far more complicated. We've got that t up on top, t all over a 1 minus t to the 8th. Yeah, you know what? How would we get that t up there? Here's how. We would just multiply the denominator. Our variable would be x. And we just have this x right here. But you know what? We're going to expand in the middle. I'm going to multiply. See, I multiplied the function by x to be able to get that. I'm going to multiply the middle representation by x. That means I'd have to distribute an x everywhere. And look at sigma. I'm going to multiply by x there as well. So what do we get? We have this x all over 1 minus x to the 8th. Distributing, you'd have an x plus x to the 9th plus x to the 17th. And I'm going to have one more power of x. This is now 8n plus 1. And that means our sigma, this x got multiplied inside. We're going to add a 1 inside of sigma there. That's x to the 8n plus 1. Wow, look at that. So right now, we are going to be able to take a look at this problem right here. We could say, well, what is the integral of t all over 1 minus t to the 8th dt? Well, it's going to be the integral of, everywhere where we had an x, it's really just a dummy variable. And forgive me, I'm going to put some bounds on here. If you look at our notes, you're going to notice that our bounds were just a slight different here. Well, you know what? Let's not even put sigma in there just yet. Our bounds, if you look in our notes, we're going to go from 0 to x. And, you know, what's going to really happen if we went 0 to x, if we represented that? Well, that's how we actually had this worked out before, being able to get a function of x. We could still do this. I think right now students can say, hey, you know, your original problem isn't going from 0 to x. Let's just see what would happen if we did that, going from 0 to x, and we'll talk about the difference that we might have otherwise. Antiderivative, this would be t squared all over 2 plus t to the 10th all over 10 plus t to the 18th all over 18 plus, this would be t to the 8n plus 2 divided by 8n plus 2. And then we'd say go from 0 to x. So right now, using the fundamental theorem of calculus, plugging in our x, we'd have x squared all over 2 plus x to the 10th all over 10 plus x to the 18th all over 18 plus x to the 8n plus 2 all over 8n plus 2. And really I wanted to say plus dot 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 in there. And you could see really what's just happened even with the sigma, but we'll deal with that. When you do the fundamental theorem, of course, you'd say minus and then you plug in a 0. Well, that's all going to be a 0. I think you can see pretty quickly that we'd go from n equals 0 up to infinity. We'd have this, look, if you were just given that, you might just say it's going to be x to the 8n plus 2 divided by 8n plus 2. And you could check plugging in n equals 0 plus plugging in n equals 1. You get that. Now, of course, what did I just do? I just represented what we would have if I had this all in terms of x, if you really think about that. So what is our answer? Well, you know, this original answer right here is just going to be in terms of t, you know, because they aren't asking for us to find a function of x. They're just asking for us to find a function of t. Everything's in terms of t right here. But I was showing you what we did in general to be able to get a function of x. Of course, right now, this also begs the question, there are materials out there that would say, hey, if you just integrated as is, wouldn't you just have a constant? You know, like if you didn't have a 0 to x here, and if you just integrated here, wouldn't you essentially get what we just had here and then say plus ac? You actually could work with that definition also. We're going to talk more in class about that. But hopefully this is enough to get you started. This right here would be the term-by-term form. This would be the sigma form. But most importantly, I hope you're getting comfortable with the two big ideas that, you know, when you have a given series, you can make substitutions and you can also multiply terms. You know, even if it's a constant, sometimes we factored out a 1/2 from a function, and then, you know, we multiply 1/2 to one of these geometrics. You know, that's like one of the examples that we did in our notes. But just as well, when you see like an x showing up, you can multiply x to this function. You multiply x to every term in the expansion. You'd even multiply x into sigma. Real quickly, I want us to take a look at number 7. But number 7, they're saying use arctangent. And sometimes they will give you, in fact, lesson 1210 is going to have us memorize some series. And this could be very, very, very helpful to not have to do as much work, building a series up. If you could start with arctangent as a fact looking like this. And so that's a very important skill that we're going to have using what we have right here. So they're saying use this, and then they want us to find a power series for x minus arctan of x divide by x cubed. So there is a numerator up here. There's really understood parentheses, and then we're going to divide by x cubed. This is not working off of the geometric series, but rather it's saying, hey, you know what? You have this as a fact. Use it. The only thing is when you're looking at this problem, you're going to say, well, wait a minute, there's a minus in front. So tell you what, let's start with that. Negative arctangent of x. What did we do? We look at this left-hand side there. It's like we're saying multiply -1 to the left side there. So that means multiply -1 to the series expansion. And I'm really breaking this down right now. Going step by step here. And you know what? That also means multiply -1 to sigma. See, all three of these things are equal. All three of these things are equivalent. And if I'm multiplying by -1 to that function there, I'm going to have to multiply -1 inside here. See, that's going to get distributed. So I'm going to say negative arctan of x. What do we get? Negative x plus x cubed. And you'd say, where are you getting the plus from? Well, -1 times this negative here. Then we get negative x to the 5th over 5. And look at this. -1 times this, we're going to have one more power. We're going to have one more power of -1. So now it becomes -1 to the n plus 1. Look at that. Let's say dot, dot, dot. But look, -1 gets multiplied inside of sigma. And we have one more power of -1. Look at that. All right. Well, then what? Then we're going to say, well, wait a minute. Now you've got this x out in front. Well, you know what? I'm going to, rather than have to rewrite everything, I'm going to do this. I'm going to say put an x right out in front here. It's as if you're saying add an x to the function. Well, you know what? I'm going to add an x right here, and I'm going to say add an x right over here to our sigma. Now, wow, this is going to look weird. This is going to look really, really weird. First of all, when you're adding an x, that's not distributing where you're going to add an x to each and every term. You just put one x on that left side. That means you put one x right over here. I hope you can see these x's cancel. Look at that. Look at that. So what do we have? X minus arctan of x. This is gone. The x and the minus x have just canceled. So look at that. We actually have something that's become a little bit simpler. Now, the weird thing, of course, is for kids to think, what's going on with sigma? Let's leave sigma alone just for a little second here. Or better yet, let's think about this for a moment. The sigma represents everything. You just lost a term. What did that adding the x do? You lost that negative x term. Where did that negative x term come from? It came from the n equals 0. So look at this. I'm going to right now say, hey, I've got negative 1 to the n plus 1, x to the 2n plus 1, over 2n plus 1. But I'm going to make a bold claim and say I lost the 0 term. Now I'm just going to have n equals 1. Double check if that's right. Plug in a 1. Look, into the negative 1, that's negative 1 to the 1 plus 1 is 2. Negative 1 squared, it's a positive 1. 2n plus 1, let n equal 1, that becomes x to the third. Down below you've got 2 times 1 plus 1, that's 3. Look, it checks out. It checks out. So if you lose a term by canceling, your counter represents that as well. So I guess what I also want to tell you, I've been mentioning this, this is so critical. The nth term is going to be showing up inside of sigma. Sigma is always that nth term, right? Well, wow, we're almost done. We've got one last thing we've got to do, and that is you got to divide by x to the third. So look at this. I'm going to divide by x to the third. And you're saying, well, I divided everything by x to the third. You know what that means? You could, if you wanted to, make a big long division here and say that's x to the third. And then you're going to say, hey, I've got to divide that by x to the third. But look, this is kind of like an I heart math, like the ultimate I heart math. Now, honestly, I don't always show that intermittent step. A lot of times I'll just jump right over here. And you could say, well, wow, what's happening? Every term you're going to divide out x to the third. You're going to take 3 x's away. And guess what? This x to the third divided by x to the third, it's just a 1/3. Look at this. X to the fifth divided by x to the third, that's x squared. And you'd say, well, I'd have negative 1 to the n plus 1. Look at this. If I have 2n plus 1 subtract a 3, you're going to have 2n minus 2. Right? Another way you could look at it is you could say each one of these get multiplied by 1 over x to the third, if you want to think of it that way. But you're going to take 3 x's away from 2n plus 1. That's where we've got that. And inside of sigma, I think you could see this just as well. You say, wow, look here, we'll have negative 1 to the n plus 1. This becomes x to the 2n minus 2. All over 2n plus 1. Now, you could double check that this sigma is generating the series that we see in the middle. And if you ever wanted to go beyond, you could see this would be what should happen for n equals 1. This would be what would happen at n equals 2. You'd say, hey, what would have happened at n equals 3? You could plug it in and see what term you'd be getting. But I hope this is helping. I hope this has made a little bit more sense for kids. And we'll talk more in class. 1210, of course, has a much more mechanical way to get power series. And we'll be talking about that very soon. So good luck, everybody.